the second session of today. Now we have, before we start, just one thing regarding lunch. We have some options nearby. So there is the cafe here at the Institute, but it might take a little longer. But there are also restaurants nearby that we can go together with you. We can show you where they are. But there is also a shopping mall that is very close by. You can go to Paulista Avenue. There is a shopping mall. You can get lunch there. And that's it. So welcome back for the second session. It's a pleasure to have Flavia Albarrac here with us. And the floor is yours. You have half an hour. Thank you.
Okay, thank you. Okay, so, and then I'm going to talk about two works we have been doing regarding combining frustrated models where you have a spiral spin liquid, and then when we add some smaller interactions, we explore with simulations and some theory and analytical calculations whether we can stabilize these topological textures, which are going to be Skyrmions and merons. Okay, so this is a large but not enough large list of collaborators whom I have been working with Skyrmions. My main collaborator is Diego Rosales, also from La Plata. The two works I'm going to talk about are with Oksana Zaharko's group in Polshar Institute and Milan Sukovic's groups in Slovakia, but we've also been working with other groups in Argentina, the one led by Eduardo Bringa, and people in France, Pierre Touchol and Ludovic Schobert. So let me define what I talk about when I talk about Skyrmions. Magnetic systems are going to be spin systems, and spins here, I know this is a quantum workshop, but are going to be classical. So a spin is going to be an arrow in 3D with some with fixed value, and the point is that the Skyrmion is a texture. Here it is a two-dimensional texture, and the colors in this sock, when regarding the spins, are going to not only make very pretty textures, but they are going to help the eye regarding the magnetization, right? So red is going to be up, so let's say aligned with a magnetic field, which is perpendicular to the plane. Blue is going to be down, and intermediate colors are intermediate magnetizations. So here you have two textures which are very similar, but they differ in the way that the arrows go from up to down in the core. And basically, if you put all the ends of the arrows together, you can show that you wrap completely a sphere. And this wrapping of the sphere is what gives these textures their topological characteristics, which can be calculated in the continuum as the topological charge. So here, if you wrap the sphere one time, you have a topological charge of either 1 or -1, depending on how you define your triple product. And it's actually this topological nature of Skyrmions is what makes them so interesting and why there has been so much work regarding them in the last decade or so. And there have been a lot of proposals of applications. One of the applications that has gained a lot of interest is the possibility of using them in data storage devices, specifically in racetrack memories, where with magnetic fields and currents, you are going to manipulate the spin textures, and you're going to either create or not a Skyrmion. And where you have a Skyrmion, you have a 1, and where you don't have a Skyrmion, you have a 0. And okay, this is very nice, but then there are also some complications. So in 2016, actually, these two papers came more or less at the same time, and they showed that when they tried to guide the Skyrmion in a straight line, which is what you would like to do if you're going to do a racetrack memory device, they showed that the Skyrmion, which here is either the black dot or the white dot, deviated from a straight line, and come to the other side of the sample, right? It turned. So basically, this is what they call the Skyrmion Hall effect, right? Because it is the normal Hall effect where the charged particles would deviate. But here it's Skyrmions, and here in particular, so here is what a Skyrmion would do. This is from a review regarding these two papers. And I know I'm Argentinian and I'm in Brazil, but I'm going to make the comment on football. If you read this review, it starts mentioning the free kick from Roberto Carlos in 1997 against France, and it compares the way the ball turns with the way the Skyrmion turns over here, right? So this is true. You can actually go and read the review over there mentioning Roberto Carlos. Okay, so this is a problem, and this has led to a lot of other proposals of how to handle other topological textures similar to Skyrmions with topological properties that would not have this Skyrmion Hall effect. Okay, so let's talk a bit about Skyrmions. So here is a Skyrmion. I actually drew this from a parametrization. There are a lot of them. You can just choose and draw them in your favorite program. And so basically this is in 2D. So here again, red is the projection. Red would be outside of the screen, blue is inside the screen, and the arrows are the components of the spin in the screen, right, in the plane. So you can see that you can either come these, so here the arrows wrap around the circle, and here they go like perpendicular. So basically this is a Bloch Skyrmion, this is an L Skyrmion, and they both have the same topological charge. And since here these spins are actually arranged in a lattice, in particular here it is a square lattice, but it could be any lattice. So what you can do is you can calculate this in the discrete space, and basically minus a factor, it is simply the triple product of 3 neighboring spins, right? So since here you can continuously go from a Bloch Skyrmion to an L Skyrmion, just moving the XY components, they both have the same topological charge. But you can also define something with the opposite topological charge, which is an anti-Skyrmion, and you can go continuously from this to that, okay? And you can draw an anti-Skyrmion in a different way, say changing the projection, and again you can't go continuously from a Skyrmion to an anti-Skyrmion, and this goes in the line of their topological properties, right? You have 2 topological sectors. Okay, and you can also, in a lattice, arrange these structures periodically, and here I was lazy, and I took the parametrization from this very nice review, which is called Beyond Skyrmions. There are lots of reviews of Skyrmions. You can choose the one you want. This one has this very nice parametrization, and basically you can show that you can build a Skyrmion lattice by a superposition of 3 helices. The condition is that the ordering vector of these helices, they have to be at 120 degrees, right? So let's do this exercise, again with your favorite program. So you can build one lattice. So this lattice is you have one lattice and you build one helix, in real space. And so this was one Q vector. So this is real space, this is reciprocal space. You have two peaks because you have Q and minus Q, but this one is a single Q ordering. Then we add one more helix, which is where the Q vector is at 120 degrees. So you have these textures, and in reciprocal space, the Fourier transform of the spins, you're going to see 4 peaks. This is a double Q. And then when you add the third one at 120, you get this Skyrmion lattice. And here, over there, you have this triple Q pattern. And why is this relevant? Because this, in reciprocal space, is what you are going to compare with neutron scattering results. And in fact, it is the way that a Skyrmion lattice was first measured a bit over 15 years ago in MNSide, where the magnetic moments are manganese. And so this is the magnetic field and temperature phase diagram. And so this thing, which is sometimes called the pocket of Skyrmions, is a region in temperature and magnetic field where they measured this pattern through neutron scattering, right? So this would be the smoking gun, that you have something like this Skyrmion lattice. This is a 3D material, so the lattices are piled up. You would have like some sort of tubes. And so at low field, at low temperature, you have helices, and then you have some sort of conical phase, and in some region this is stabilized, and the next year these skyrmions were measured in real space, in a quasi-2D material, where again you can see this is quasi-2D, the skyrmion lattice goes to even lower temperature, but again you have helices, skyrmions, and then everything is field polarized. And here is, so if you can read over here, there it says experimental phase diagram. This one is the theoretical phase diagram, which is basically calculated with Monte Carlo simulations for a very simple model, which is over here, but let's go a bit into that. So this model is a Hamiltonian, nearest neighbor Hamiltonian, where you have ferromagnetic exchange couplings, an in-plane Dialoghinsky-Morisha, and then you need a magnetic field to stabilize these skyrmions. This in particular is in the square lattice. The way you put your in-plane Dialoghinsky-Morisha will tell you whether you have Bloch or Snell skyrmions. And these are actually some simulation results I made in particular for a certain value of the couplings. And if you're doing simulations, you need an order parameter. And the order parameter to build this sort of density plot is simply the scalar chirality. Okay, so where you have a non-zero scalar chirality, you have an indication that you have a skyrmion lattice. Okay, so talking about simple models, then you could, here this is in the square lattice, but I could do it in any lattice. The thing is, I could also think what happens if I change ferromagnetic couplings for antiferromagnetic couplings, and there the lattice is important, right? Because it is not the same to have an antiferromagnetic square lattice or a triangular lattice, where for antiferromagnetic couplings we have a frustrated system. And in fact, about 10 years ago now, Diego Rosales and collaborators, they found that in the triangular lattice, for a certain range of magnetic field at temperature, the texture that was found was something like this. Again, this is with simulations. You can see this is antiferromagnetic, right? Because you have red and blue together. So basically, at nearest neighbors, the exchange coupling wins, and you have an antiferromagnetic order. But then what you can do is you can split these textures in 3 sublattices, and each of these sublattices is a ferromagnetic skyrmion lattice. So basically, what they found was an antiferromagnetic skyrmion lattice formed by 3 interpenetrated ferromagnetic lattices. And why are antiferromagnetic skyrmions interesting? Because it's one of the proposals of how to avoid this skyrmion Hall effect. And in fact, regarding proposals, there are a lot of textures that have been proposed. Over there is the anti-skyrmion. Here is a model for antiferromagnetic skyrmions. Again, this very nice picture is from that review I mentioned. And among these many textures is the other one from the other ones from the title, which are the merons. And a meron is basically half a skyrmion. Okay? It's simply that. So if a skyrmion wraps around the sphere 1, the meron wraps around half a sphere. So if a skyrmion has a topological charge of -1, the meron will have of -1/2, and the antimeron of 1/2. So the way you arrange a meron depends whether you can have the core pointing down or pointing up, and then depending on how you draw the x, y, so the in-plane components of the spins, you will either have a meron or an antimeron, okay? And again, you can also build a lattice with a very simple parametrization. So you needed 3 helices for a skyrmion lattice. For a meron, you need 2 helices. And the condition is that these 2 helices have perpendicular ordering vector, right? They are at 90 degrees. So this is actually a meron antimeron lattice. And you can see in reciprocal space, you will have like this square, because the cube ordering vectors are at 90 degrees. So this would be the indicator that you have some meron lattice if you will look to this in a neutron scattering experiment, okay? So you have a lot of double Qs here. The particular thing is that the peaks are at the vertices of a square. And these merons and antimerons were measured in real space in 2018. And the thing is that in this work, there is not a proposed Hamiltonian, but basically they showed that they can go from a helical state to a skyrmion lattice, and in the middle, they go through this sort of texture that here you can see. So here it's N, but it's basically Q, the topological charge. And you can see like many different ways to have merons and antimerons. And this particular texture is an array of merons and antimerons, and in the middle, right here is the unit cell, the magnetic unit cell. In the middle, you also have some merons. So if you do the calculation, the topological charge of the unit cell is 1, so it makes sense that you can go to this, from this to a Skyrmion lattice, right? So the topological charge does not change, which is important, right? So you have to maintain the topological properties. And they have actually been also proposed a combination of merons and antimerons to avoid the Skyrmion Hall effect. This is just one example of a paper from last year where they propose that for a bilayer van der Waals system with different Dielorzynski-Morisha, you have textures of opposite chirality, and in that way, you will cancel out the Skyrmion Hall effect. So, okay, so where do we come in, actually? So we work in mainly doing theory and simulations. I will show you some work regarding comparison with experimental results. And one of the things we do is we try to propose different models to get different exotic textures regarding, for example, antiferromagnetic skyrmions and merons. And then we also try to study how we can manipulate this region in the phase diagram, whether we coupled it to other topological textures as spin liquids, or we manipulate them with distortions and deformations. And we have also been using machine learning to explore these phase diagrams and to distinguish between this type of textures. But here mainly, I'm going to focus on talking of how we start from spiral spin liquid models, and then we get some of these exotic textures. So the first work is regarding this material, which is a 3D material where manganese lies in a diamond lattice. And it is well known that in the diamond lattice, even for ferromagnetic nearest neighbors, if you go to second nearest neighbors antiferromagnetic, the lattice is frustrated, and for a range of J2, J1, J2 being the exchange couplings, you will have a spiral spin liquid. So what is a spiral spin liquid? In a spiral spin liquid in reciprocal space, you don't see Bragg peaks, you see a degenerate line, right? So if you have that in a neutron scattering experiment, it gives you the idea that you have a spiral spin liquid. And in fact, Oksana Zaharko's group in 2017 published these neutron scattering experiment results, where at 2.9 Kelvin, they in fact saw that here you don't have Bragg peaks, you have these lines. So indeed, this material was a spiral spin liquid at that temperature. The thing was that they could lower the temperature, and when they lowered the temperature, they saw some selection of peaks. So that means that you have these J1, J2 models, but then you have to have additional interactions that will be smaller, and they kick in when you lower the temperature. And that is actually where we came in La Plata. And what we did was we proposed a model which is a bit complicated because, you know, you can propose a lot of models, but the thing is getting them to match the experimental results, right? So the model here is basically a J1, J2 interactions with additional J3, and then the added couplings are, so it's basically an anisotropic interaction, which is more or less like the dipolar interaction for first nearest neighbors only, and some anisotropy. And so the phase we found is a bit complicated. This is for magnetic field along the 1, 1, 1 direction, so in the diagonal of the cube. And let me remind you that in the diamond lattice, the planes perpendicular to that direction are actually triangular sublattices. So there we also find 3 interpenetrated textures, so that is why this is called over there antiferromagnetic. And it's called fractional because if you look at the textures over there, here are like, would be the projections in the sphere, you can see that they do not completely wrap the sphere. So they are not completely skyrmions. You could think of them also as maybe they are almost merons. So this is why they are called fractional antiferromagnetic skyrmions. So antiferromagnetics, yes?
How large are the spins in the merons?
Sorry?
The spins in the merons, how large are they?
I think it's 5 halves, okay? But the classical description works very well. Actually, for most materials, the classical description is works well enough to explain the experimental results. Okay, So here is a comparison actually of the experimental phase diagram and our phase diagram from simulations, which is constructed again with the order parameter, which is the scalar chirality. There is a very good agreement, and also when we study where over there, so the squares over there are the intensities of the Q vectors obtained from neutron scattering, and we compared with the intensities obtained from our results. And we also studied how these change when you change the direction of the magnetic field, luckily, successfully. So what we can say is that in this material, you can go from a spiral spin liquid, and when you lower the temperature, you get this fractional antiferromagnetic Skyrmion lattice. So there have been other materials where spiral spin liquids arise, in particular in not two-dimensional materials, but in materials where you can model them as a honeycomb lattice. And so in the honeycomb lattice, it is well known that J1, J2 model antiferromagnetic couplings, both of them, you have two types of spiral spin liquids. So you can either have this type of spiral spin liquid where the lines are around the gamma point in the Broulan zone, or this type of spiral spin liquid where the lines are around the K point. This is for lower J2, and this is for larger J2, okay? And as you see, the experimental evidence shows that there are materials where you have these two types of spiral spin liquid, depending on the material, right? So this would be like the first type, and this is the second type. Okay, so then let's inspire ourselves from the other work. And what we said, okay, let's go to the honeycomb lattice, to this J1, J2 model, and let's add a small interaction to see what happens if we can see these topological textures. And our idea here was to go, let's say, the easy road, and let's add a Dzyaloshinski-Morisha, right? Because I know that if I have an in-plane Dzyaloshinski-Morisha, there is a good chance to have Skyrmions. So here the Dzyaloshinski-Morisha, this is important, it's like 10% the value of J1. And since this is the honeycomb lattice, you have two triangular sublattice, you have to have the Dzyaloshinski-Morisha to second nearest neighbors. Okay, so this is the work we were doing with Maria Mohilna and Milan Sukovic from Slovakia. And the idea to have a small interaction would be that, okay, so in the pure Heisenberg model, you have a line. And then if we add interaction, so maybe this line is a bit distorted, you will have minima. But with thermal fluctuations, you will retrieve this spiral spin liquid behavior, right? So you will erase the minima because you have enough energy to not see it. And this is what happens. So here, over here, you can see that we get this second type of spiral spin liquid with simulations. This is for a strong ratio of J2, right? So our strong second nearest neighbors interactions, which are the interactions in the triangular sublattice. And in fact, what we find is that for each triangular sublattice, we have these antiferromagnetic Skyrmions. This is nice, but if you work in this, you could sort of predict it, right? Because you had second nearest neighbors interactions in the triangular sublattice, the Dzyaloshinski-Morisha is in the triangular sublattice, so it is expected that you will get the same behavior as in the antiferromagnetic triangular model. So this is nice, and again, the selection of triple Q is basically a selection, of course, along these lines from the spiral spin liquid. And the interesting thing comes in when we go to lower values of J2, where the spiral spin liquid is this one, the one which has circles around the gamma point. And again, in our model, there is a selection in these gamma points, which is actually a triple Q, but with temperature, you erase this selection, and you basically see the spiral spin liquid. Okay, so for a certain range of temperature and magnetic field, we have this intricate texture over there. So these textures, you divide it in two, and when you go into each triangular sublattice, you see like this here, these blue and red textures, right? This is the local chirality density, and these textures are actually merons and antimerons. So here again is a description of the different types of merons and antimerons we have. So you have a meron and an antimeron, and in the middle you have like smaller merons. Again, this is a discrete lattice, so they will not get very well formed, but when you look at the local chirality density, you have the idea of that is going on. And again, the interesting thing here is that you can confirm this when looking at reciprocal space, because you will get this double Q pattern where the Qs are at 90 degrees. So to our knowledge, this is, I mean, there have been some works where they have realized meron lattices, but this is one of the first where we get merons and antimerons. And again, this is a different lattice, and this is antiferromagnetic, but the texture in each sublattice is very similar to the one I showed you before. You have the merons and antimerons, and in the middle, you have these tiny or smaller merons, which make that the unit cell has a net chirality. And the other interesting thing is that when we start to destroy this meron-antimeron lattice, when we put a magnetic field before going into a field polarized phase, we see this texture where you can find, so here to help the eye, there are these circles where you find these things. And when you look closely into them, you zoom in into each sublattice, you see that these textures are actually meron-antimeron pairs that are bound, okay? So you can't destroy the meron-antimeron pair. If in one sublattice you have a meron, in the other sublattice you will have an antimeron. So this is a disordered phase, so we would call this a gas, and the textures are bound pairs of merons and antimerons, which again is a very unusual phase to find in with these classical Hamiltonians. Okay, so to sum up, I basically talked about skyrmions and merons in spin systems, and I wanted to focus on two works where the line of work is the same, right? Let's say if we start from a spiral spin liquid and see what happens when we add small interactions to see if we can realize these sort of exotic textures. So in one case, we have this J1, J2 model in the diamond lattice, which is experimentally very relevant. And with additional, so it has been shown that at higher temperatures, you have a spiral spin liquid. We add some interactions, and we see that for a certain range of magnetic fields, we get an interpenetrated antiferromagnetic lattice of fractional skyrmions. And this, in fact, was one of the first realizations of antiferromagnetic skyrmions in experiments. And then we propose a model where we start with a spiral spin liquid in the honeycomb lattice, and adding a bit of the Aloszynski-Morisha, we do not only find antiferromagnetic skyrmions, but we find these patterns of merons and antimerons in each of the two triangular sublattices. Okay, thank you.
Thank you very much, Flavia. It was a very nice talk. And we have time for questions.
Hi, thank you very much. I would like to know which one of your parameters control the core size of the magnetic texture, and if this has anything to do with the forming a square lattice or a hexagonal lattice.
Okay, this is, oh, I don't know how to go back. Okay. Okay, so basically in a simple model, so it depends on the model, right? But in a very simple, in the simple model for a skyrmion lattice, basically the ratio between J and D will give you the size of the skyrmion. And you can very easily play with that. And for example, so this is for D and J are actually the same, and that will give you the idea of the size of the skyrmion. And then you usually have triangle. So the thing whether you have a square lattice of skyrmions or a triangular lattice of skyrmions is not trivial. You usually have triangular lattices. And now, in the same way that we start to explore whether we can get a meron lattice, there are works exploring whether you can go and have a square skyrmion lattice. But usually you will get this triangular lattice of skyrmions.
Thank you.
More questions?
Thanks for the talk. So when you compare the neutron scattering data and try to distinguish between single queue and triple queue, how do you account for domains of the single queue in the analysis?
That is a a very good question, actually. And I think it was actually an issue in this work. So I do not work in the experimental part, so I cannot assure, but if you... so basically here, again, yes, you could have this triple queue phase and it could be single queue domains. But at least to my knowledge, they were pretty sure that you should have triple queue. So this is a single crystal neutron scattering, and you should have a clear triple queue ordering. There were no domains. But it is
No, what I'm asking is how do you distinguish that from single queue with domains? Because single queue with domains would also have 6 spots, 6 different
yes,
spots.
I understand what
Yeah.
you mean. The thing is that experimentally, I'm not sure exactly how they did it. This is one issue. Of course, with the simulations, it is very easy to see, right? Because you can go and you can look in the kitchen and see what is going on, right?
Okay, thank you.
More questions? We still have some time.
Oh yes, most of the time. They are not commensurate, actually. They're incommensurate queues. And the thing is that, okay, so I can answer from the... So yes, this will be an issue if you have borders in your sample, for example. Or when you work with simulations, you usually work with periodic boundary conditions. So they accommodate. And yes, you have to do studies of what happens with system size, and you can also study what happens if you add borders and stuff like that to see what happens with the size of the Skyrmions. But usually they really do not change. I mean, you will not have significant changes with that.
So then, just in principle, will these cases then remain gapless even when you add all perturbations? Because if there is no commensurability,
Yes.
the Goldstone modes should remain gapless, right? Is that the case here? Or
Okay, so this is everything is classical here, right?
but you can still
Yes.
do Goldstone modes even classical.
But yes, and the thing is that this would be, yes, they would be incommensurate. And
Even the question is, all these Tsioloshinsky-Mori and other spin orbit coupling will not gap out the Goldstone modes, right? Is that known?
okay, I think not, but okay.
The Dzieloszynski-Moria can
break.
gap out if they are staggered. But if you have a uniform Dzieloszynski-Moria, it forms a spiral, and the
And then you go
combination of
into the other
spirals
one.
then give rise to a skyrmion.
You need a magnetic field.
No, they're not.
You need a magnetic field to get the Skyrmions, right? In these models. There are other models with additional interactions that propose that you might get Skyrmions at no field, but
Do we have more questions? If not, let's thank Flavia again.
okay, thank you.
Thank you, Flavia.